Okay, so Physics 11, this is a continuation of our new unit on dynamics. So today what we're going to be talking about is Newton's three laws, and these are huge when it comes to anything physics related, especially when it comes to dynamics. We'll be talking a lot about forces, we're going to be talking about free body diagrams, things that you are going to use in any other physics course that you would ever take, okay? So this is a big lesson, it's got quite a few examples in it to discuss, and we basically use the stuff that we talk about today as we go through almost every other section in this course, right? So just keep that in mind as we kind of get into this. All right, so we first talk about Newton's three laws, okay, which you should know, right? So these should all go in your vocab journal. So when we talk about the three laws, the first law, Newton's first law is that an object at rest or in uniform motion will remain at rest or in motion unless acted upon by an outside force, right? So that's an object at rest will remain at rest unless we actually apply a force to it to get it to move, and an object in motion will remain in motion, right? So if it's already moving, it's going to keep moving unless, again, we act upon it with an outside force. And that outside force could just be friction, right? A force of friction that slows an object down, right? Or if we apply the brakes to something like a moving vehicle, that again is a force that's acting upon that, okay? So that's Newton's first law. Newton's second law is that the relationship between an object's mass, acceleration, and the applied force is equal to mass times the acceleration, okay? You might recall from last lesson we talked about how a Newton was defined as the amount of force required to get a 1 kilogram object to accelerate 1 meter per second squared, right? And again, this is where these units are coming from, right? It's a mass multiplied by its acceleration, right, which will give us units of newtons of kilogram meter per second squared, okay? So that's what Newton's second law is saying. And Newton's third law, which you've probably heard before, is that for every action there is an equal and opposite reaction, right? So if we apply a force in one direction, there is an opposing force happening in the other direction as well, okay? So we do need to think about that as we start looking at these options. So this is what we talk about when we talk about a free body diagram. Huge. You see these a lot in physics, right? So a free body diagram is just a graphical illustration which is used to visualize all of the forces that are acting on an object, okay? So when we draw a free body diagram, you don't have to draw like the actual item, like you don't have to draw this person on a bike. You can typically just draw a dot, right? So I'll just kind of show you that on the video wise. But if we're talking free body diagram, right, I might have an object here, and I can just draw it with a dot, and I can say, okay, this object might be in, there's gravity acting on it, right? So the force of gravity might be pulling down on that force. Perhaps we're moving it, we're pushing it forward, so this would be considered an applied force, right, being pushed towards it. Right? You also have something called normal force, which happens perpendicular to the object which something is resting on. So this is typically perpendicular, or typically opposite to force of gravity if something's resting on a flat plane, right? This is what we would call normal force. And then something that if we're trying to like maybe move something across, you might have the force of friction, right? And you just kind of are using subscripts to kind of show, right? So if it's an applied force, we see Fa. If it's something like gravity, force of gravity, right, which we used in our last lesson on calculating weight, right, which was mass times gravity, right? And then we'll have force of friction, which we'll talk about more in detail in a later lesson. And you could have force, what we call normal force. You could also have something like a force of tension, right? So perhaps gravity might be pulling down, but you're like suspending something on a string, so the tension in the string is a force that's being applied in an upward motion, right? So depending on the forces that are at work, you're showing all of these and in which direction they're moving, right? Which direction those forces are being applied in your free body diagram, right? Not all of these forces are always at play, right? You might have a situation where you just have a force applied and a force of friction, and because it's resting directly on a surface, these are really the only forces that are at play, right? Or if you're thinking about like suspending an object, right? You're not trying to move it, you're just trying to hold it. You might have force of gravity that's pulling it down, but you might be having a force of tension that's pulling it up, right? So they're not always, all four arrows. It's depending on the situation that you've been given, okay? But this is what we just call a free body diagram, right? Where you're showing the mass, right, of the object. You can just use that with a circle, and then you're using arrows, right? So like vectors to show, okay, which forces are being applied, okay? So that's what we're talking about when we talk about a free body diagram. Okay, and again, it's used to visualize all of the forces that are at play there. All right, so there may be 4 forces acting on an object. So like I said, not every situation is going to have them. For the purpose of this next lesson, things that you'll want to think about is, like I said, an applied force. So a force which is constantly pushing an object along. Typically that's horizontally, right, where something's sitting, like lying on a surface and we're pushing it horizontally. Your force of friction, which actually slows down an object, so it will actually go against, so it'll be going in the opposite direction of your force of friction, or sorry, of your force that's being applied, right, because it's acting against the force that you're trying to push forward, it's holding it back, okay? You could have a force of gravity, right, in which, something is being drawn further down towards the ground, right? And then you can have normal force, which is defined as a force that's perpendicular to the surface that an object contacts, okay? So if that object is just on a flat surface, it's going to act vertically, but if you're like pushing a book up against the wall, right, that force actually comes out towards you. Right? So if you're like pushing something against the wall, again, the object the surface is resting on is a wall, so the normal force acting perpendicular on that is going to come out towards you. Okay? So again, there's another example of like a free body diagram, right, where you're seeing all those like applied force, force of friction, normal force, and force of gravity. Right? Again, you don't have to draw the actual 10 kilogram mass. A circle is fine to show that. Okay? So with Newton's second law, we basically come up with this formula where F is equal to ma, right? So force is equal to mass times acceleration. Now, a big thing to note here, though, is that when we're talking about force is equal to mass times acceleration, it's the net force, right? So that means the sum of all of the forces acting on a particular mass is equal to the mass multiplied by the acceleration of that particular object, okay? So even though you're not necessarily seeing net, we could write it in little subscripts underneath there, but the net force acting on an object is equal to its mass multiplied by its acceleration. And again, when we first started this unit, we talked a lot about having to, not this unit, sorry, we started this course, we talked a lot about needing to be able to manipulate formulas because, again, you can do that here and you say, well, the acceleration would then equal force divided by mass, or mass would equal to force divided by acceleration, okay? And again, just noting that net force will be net horizontal force or net vertical force, depending on the problem in this particular case. All right, we're starting out relatively easily. We will eventually get to force at an angle, but for right now, our net force is just going to be, okay, well, what's acting in the horizontal and what's acting vertical? I won't be giving you stuff at angles at this point in time. Okay. So again, when solving those questions that involve an applied force, mass, and acceleration, remember that any scenario that involves a suspended object, like an elevator, and that something's going to be moving up and down vertically, that's going to have a force of gravity to consider as well, okay? And this will often tie in with the applied force and will result in a net force, okay? So again, that's that idea of seeing that net force where, you need to think about all of the forces that are acting upon that particular object, and then finding the overall net force, okay? So what we're going to do is we're going to go over quite a few practice problems, okay? So trying to give you a few different scenarios that you can start thinking about. So let's just talk a basic one to start with, okay? So practice problem number 1. So we have a force of 192 newtons is applied to a 12.5 kilogram object along a horizontal frictionless plane, okay? Calculate the acceleration of the object. So we'll start with that. Okay, so with these types of problems, we should always get in the habit of trying to draw that free body diagram. So here's our mass. It's being pushed, right, by a force, by an applied force. We've been told that it's frictionless, which means there's not going to be anything resisting it and pulling it backwards, right? If it's resting on a surface, then force of gravity isn't really going to be at play here, okay? So it's not combining to the net force. So what we have is that the only force being applied is that 192 newtons. So all of the forces added together is just 192 newtons. So what we have, again, listing our variables, our mass is equal to 12.5 kilograms, our applied force is 192 newtons, and that's actually also our net force, right? It's the only force acting on it, so it's the sum of all of the forces. The formula that we're using is force is equal to mass times acceleration. We've been asked, well, what is the acceleration? So I can rearrange this equation to get acceleration by itself, so I can divide both sides by m. So F divided by m is equal to A. So I take my force of 192, I divide it by my mass of 12.5, that will be my value for my acceleration. When I do that, I get 15.36 meters per second squared. However, with sig figs, I only get 3, so this would round to 15.4 meters per second squared. Okay, so there's probably one of your simpler ones, just because it only involves one force. Okay, let's move on to sample problem number 2. All right, so there's your solution, and here we go. All right, so here's sample problem number 2. So in this case, we have a 1.35 kilogram ball pushed along the ground. It starts from rest and is pushed a distance of 9.3 meters, increasing its velocity to 21.4 kilometers per hour. Determine the force that is acting on the ball. Okay, so what's interesting about this question is the fact that we don't actually have the force, nor do we have the acceleration, right? But in order to find the force, it's mass times acceleration. So we need to figure out the acceleration. So we actually go back and we use our work that we had done in our previous unit on kinematics, and we can use one of our big 3 equations to be able to determine the acceleration of this ball. All right, so again, let's see what this looks like. All right, so what we have is we just have a ball that's being pushed along, again, a frictionless surface, okay? So we're still just dealing with a single force, okay? It's on a surface, so it's not being pulled down. Again, we're assuming it's a frictionless surface, so it's done. So here's the information that we have, right? So easy little free body diagram, single force being applied. We have the mass of the ball is 1.35 kilograms. We know it's being pushed from rest, which means its initial velocity is 0 meters per second. We know that it's being pushed for a distance of 9.30 meters. We also know that it's being pushed until it reaches a velocity, so its final velocity is 21.4 kilometers per hour in a positive direction. But remember, when we're dealing with things with velocity, distance, and acceleration, we need to have this in meters per second. That's our standard value, right? So what we need to do is we need to convert this 21.4 kilometers per hour and put it into meters per second. So we do that just by dividing it by that 3.6. So our real value for VF is really just 5.94 meters per second. Okay, again, in the positive direction. Okay, so that's what we're dealing with right there. Okay, so we've got our mass, we've got our initial velocity, our final velocity, and our distance. What we're trying to find is the acceleration. So we look at our kinematics equation, we say, all right, well, we know that there's an equation that relates VI, VF, and D, and it is VF squared is equal to VI squared plus 2AD, right? And we can use this to be able to solve for A, okay? So we rearrange that formula, we subtract VI squared from both sides, so VF squared minus VI squared, and then we would divide by 2D. That would equal A. So we use that 5.94, so 5.94 meters per second squared minus the 0 meters per second squared divided by 2 times 9.30 meters, right? So we can do all of that. That will equal our acceleration, okay? So when we do that, we get a value of, so I just do all that in one step in my calculator, and I get a value of the acceleration being 1.897 meters per second squared. But again, we're really only limited to 3 sig figs, so we'll call that 1.90 meters per second squared. okay? So that's going to be what we're going to use for our acceleration. So now that we have the acceleration, we can use that to go and find our force, right? Because again, force is equal to mass times acceleration, and we have the mass of 1.35. So what we can do is take our 1.35 and multiply it by our acceleration of 1.90 meters per second squared. So force is equal to 1.35 kilograms multiplied by 1.90 meters per second squared. And what we get is a force of 2.57 newtons. Okay, and again, force is still a vector, so in this case it's still being applied in the positive direction. Seeing as that the velocities were moving in a positive direction, then so would the force applied. So we can just add a little positive after that to indicate that that is in fact a positive force acting on the ball. Okay, so again, just because we're in a dynamics unit doesn't mean that we forget about our kinematics work. So if we don't have acceleration given to us, it doesn't necessarily mean we don't know how to find it. We can just go back to our work with kinematics and figure that out. Okay, practice problem number 3. All right, so changed up a little bit. So in this case, we have a man riding an elevator. The combined mass of the man and the elevator is 7.00 times 10 squared, or essentially 700 kilograms. Calculate the magnitude and direction of the elevator's acceleration if the tension in the supporting cable pulling up is 7.50 times 10 to the 3 newtons, or essentially 7,500 newtons. Okay, so again, free body diagram to start. So let's do that. So in this case, it's a little bit different. We have our elevator and person mass here. We have gravity that would be pulling it down, so that you have force of gravity acting down, but you'd have a force of tension pulling up on the elevator. Okay, so telling us that the force of tension in the rope is there. Okay, object is not resting on a surface, right? It's being suspended. So therefore, we don't have any sort of normal force that we need to worry about, right? So you get force of gravity pulling down, force of tension pulling up. Okay, so in that case, what we need to look at is what variables do we have? Well, first of all, we have that our force of tension was given to us at 7.50 times 10 cubed newtons, okay, and again, that was pulling up in an upward direction, so it's like a positive value. We have the mass of the elevator and the person combined at 7.00 times 10 squared kilograms, okay, and we've been asked what's the acceleration, okay, and signs will be very important here because if we get a value where the acceleration is positive, then that means the elevator is in fact moving in an upwards direction. But if we get a value where the acceleration is negative, it would mean that the elevator is moving in a negative direction. So this is our first problem where we actually have two forces that are being applied to the same mass. So this is where we come into this idea of a net force. All right. So our net force is a combination of the forces acting on the object, and in this case, they're acting in opposite to each other, right? So we'll need to assign one as positive and one as negative, right? So the net force is the sum of the forces, so it would be Ft plus Fg, right? The force of tension plus the force of gravity. However, the force of tension is, well, again, we can assign this as positive and this as negative, so the force of tension is acting in a positive direction, whereas the force of gravity is acting in a negative direction. So what we would have is we would actually take our value of our force of tension, and we would have to subtract our force of gravity, right? Because they're being combined. So we do have a value for force of tension, which is that 7.50 times 10 cubed newtons, right? And we're saying that that's positive, okay, because it's acting in the positive direction. Now we need to add a negative force of gravity or subtract our force of gravity, okay? But you'll notice we weren't given the force of gravity, but in our last lesson on weight and mass, we learned how to calculate it, where F of g, force of gravity, is equal to mass times gravitational acceleration of the Earth, which is 9.81 meters per second squared. So we can calculate force of gravity, take our mass of 7.00 times 10 squared kilograms, and multiply it by our 9.81 meters per second squared. okay? When we do that, we get a value of 6,867 newtons. Okay, so going back to our net force acting on this object, we have our force of tension pulling up on the object, our force of gravity pulling down on the object, so we would need to subtract that. Okay, so I take my 7.50 times 10 cubed newtons, subtract my 6,867 newtons, to get that my net force acting on this object is 633 newtons. And notice that that's a positive answer, right? So that means that if the overall net force is positive, it must mean that the force of tension is bigger than the force of gravity, which would indicate that our elevator is moving up in this scenario. Okay, but we've been asked for the acceleration. So again, now we go back to our formula. I'm just going to erase some of this now so we have space to write it, where we use Newton's second law, which is that the net force is equal to the mass multiplied by the acceleration. To get the acceleration, we would take our net force and divide it by our mass. And we have both of those values of 633 newtons divided by our mass of 7.00 times 10 squared kilograms. And when we do that, we get a value of 0.904 meters per second squared, and again, we note that that is happening in a positive direction. So in this scenario, our elevator is moving up with an acceleration of 0.904 meters per second squared. Okay? All right. Oh, I didn't need to escape that one. Just go back to our slides. Okay, so there's practice problem number 3. Now we move on to 4, right? So like I said, we're going to do 5 of these just to kind of show you a bunch of different types of examples that we'll be dealing with here. So here's number 4. An object has a mass of 9.45 kilograms. It is pushed along a horizontal surface with a force of 62.6 newtons in the positive direction and is met with a force of friction that has a magnitude of 42.3 newtons. Okay, so your force of friction is resisting motion, right? So it would be acting opposite to your applied force. Calculate the acceleration of this object. Okay, so in this question, the force of friction is given to us. In a later lesson, we will in fact actually be using how we actually calculate force of friction. Okay, but we're not going to do that right now. Right now, it's just given to us. Okay, so again, we go back to our free body diagram. Okay, so what we have is our object that is, we have an applied force is being acted on it in a positive direction, and we have a force of friction that is acting against it, right, moving in the opposite direction. So again, we can consider this moving to the right as positive and moving to the left as negative, okay? So other information that we have that the mass of this object is 9.45 kilograms. We have that the applied force has a value of 62.6 newtons acting in a positive direction. And we've been given that it's being met with a force of friction, which would be acting in the negative direction, as 42.3 newtons. So we'll assign that as a negative. Okay, we've been asked what is the acceleration of this object. Okay, so again, in order to figure that acceleration out, right, what we'll want to be using is F net is equal to mass times acceleration. So what we need to solve here, we have the mass. We need to figure out what is the net force acting on this object. So again, our net force is the sum of the forces acting on the object. So we have, in this case, the force applied and the force of friction. The force applied was 62.6 newtons acting in a positive direction, and the force of friction of 42.3 newtons, but acting in the negative direction. So really, it's like we're adding a negative, which is the same as subtracting. Okay, so when we do that, we do the 62.6 newtons minus the 42.3 newtons, and we get a value of 20.3 newtons here. Okay, so there's our net force of 20.3 newtons. That's the value, and again, that's positive. Okay, that's the value that we then assign to here, right? So what we get, we're looking for acceleration. So we would take our F net and we would divide it by our mass, to get acceleration. So we have 20.3 newtons, and we divide it by our mass of 9.45 kilograms to give us our acceleration. And when we do that, we get a value of 2.15 meters per second squared. That is the acceleration of that object if we are applying a force of 62.6 newtons and the force of friction kind of pushing against us is 42.3 newtons. That will allow us to move the object at an acceleration of 2.15 meters per second squared. Okay? All right, let's go and take a look at our last example here. Okay, so practice problem number 5. So in this one, we have a curler that exerts an average force of 9.5 newtons south on a 20 kilogram stone, assuming that the ice is frictionless. Okay, so we're assuming that there's no friction acting against our applied force. Okay, we know that that's not really true, but for the sake of this problem, let's assume that the ice is frictionless. Okay, because if it was frictionless, you would just keep going. Okay. The stone started from rest and was in contact with the girl's hand for 1.86 seconds. Determine the average acceleration of the stone. Okay, so let's take a look at this one. All right, so what we have, again, free body diagram, you've got your curling stone, and there's being a force applied moving in a southern direction. That's here. Okay, that's really all we're having because, again, we're assuming from the question that it's a frictionless surface, so there's nothing pulling against it. It's on a surface, so gravity's not pulling it down. This is just kind of what's happening here. Okay, now information we have is that mass is equal to 20.0 kilograms. We know that the average force applied was that 9.50 newtons happening in a southern direction. We know that it started from rest, so its initial velocity was 0 meters per second, and we were given information here about time, right, where it was in contact with the girl's hand for 1.86 seconds. Okay, so for part A, we're being asked what is the acceleration of this object, and really we can do that straight from just our F is equal to ma, right? We have the force, it's the only force being applied, so our Fa is our F net. We have the mass, and we can solve for the acceleration. So the force divided by the mass will, in fact, equal the acceleration. So we just need to take our 9.50 newtons and divide it by our 20.0 kilograms, and that gives us an acceleration of 0.475 meters per second squared in a southern direction, right? Because it's in the object of motion. So there's our answer for A, right? If we go back and take a look at what part B is asking, it's saying determine the velocity of the stone when the curler releases it. So again, this kind of comes back to our stuff with kinematics. Okay, so again, what we have now is we have VI, we have acceleration, we have T, and now we're looking for VF. Right? And again, we have an equation that helps us with that. We have that VF is equal to VI plus A times delta T. Right? And this is just a matter of plugging in those values. Our VF is equal to our VI of 0 meters per second, plus our acceleration that we just calculated using the force of 0.475 meters per second squared, multiplied by our time of 1.86 seconds. All right? And then we just multiply those and get a final velocity of 0.884 meters per second, and again happening in a southern direction. Okay, so again, we're still using force, but we're also using our kinematics equations throughout this as well. All right, so those were the 5 practice problems I wanted to go over, kind of showing you some of those examples. There's a bit of work that I'd like you to practice with this, okay, just like with a lot of stuff we've been doing with physics, every type of question is slightly different, so you want to be able to expose yourself to as many different types of questions as possible so you kind of get practice in determining what forces are being applied and which ones are relevant to the situation and which ones are not. Okay, so you've got some textbook questions. Again, I'll just upload the PDF document of the screenshot of those pages because this won't correspond to your textbook. And there's also a set of worksheets, problems that you would want to work on as well, okay? And that's kind of where we're at now, and I will not be posting a new video for you to look at until Tuesday at this point, so you can kind of have a bit of today to maybe work on it. If you've got time over the weekend, you can do that, and then you'll have Monday to work on that as well, and you won't get anything new now until Tuesday, okay?